Hey folks, how's it going? Mr. Murray here, coming to you with a recap of the backside of handout 4.9, where we're going to take a look at a couple of examples of absolute value inequalities, contrasting the graphs with the solutions. We're going to be taking a look at not only the algebraic components, but also the graphical kind of interconnection there. All right, so just to recap, this is what your top of the front side should more or less look like. Your example formulas might be a little bit different depending on if you were A period or C period, because we came up with that using student input. So here we go. So to begin, we have this graph right here. We're going to start with the first one. Absolute value of x plus 1 is less than 4. 1, 2, 3, 4. So we've seen in that square up on the front of 4.9 that the solutions have to do with the intersection between this horizontal line that represents y equals 4. Make that a little bit thicker. And the graph of the absolute value function itself. So we want to know, when is it less than or equal to 4? 1, 2, 3, 4. So what we have is, here we have x is equal to 3, and here we have x is equal to negative 3. Okay, so here's x is equal to negative 3, and here's x is equal to 3. So that's where the functions are equal, and if we were solving an equation, we would actually be done at this point. But we want to know, where is x, where is this thing x plus 1 less, that is the absolute value of x plus 1 in any case, where is it less than or equal to 4? So we can see that between negative 3 and positive 3, the absolute value of x plus 1 is less than 4. And I'm going to go ahead and shade this using my tablet here. So we should expect basically our solution to be negative 3 to 3, and we're going to go ahead and we're going to put that in brackets because negative 3 and 3 could actually be solutions. How does it look algebraically? So what we're going to do is we're going to go ahead and we're going to get the bars alone, because that's how we always start, by subtracting 1 on both sides. And the absolute value of x is less than or equal to 3. So if we think about what numbers could work, okay, so 3 could work because the absolute value of 3 is 3. 2, 1, and 0, those absolute values are less than 3. And also negative 1, negative 2, and negative 3. Those kinds of absolute values are also going to be, that is the absolute value of those numbers, are also going to be less than or equal to 3. But numbers like 4, 5, and 6, and negative 4, negative 5, negative 6, for example, those have absolute values of more than 3. So those would be examples of numbers that we would not include. Okay, so what we'll do is, this is an and inequality. So we're going to say negative 3 is less than or equal to x, which is less than or equal to positive 3. Okay, again, the front side of 4.9 will give you a sense of how you can determine what kind of inequality, like an and inequality, you're going to have based on the fact that the bars, the inequality is pointing away from the bars and towards a number. Okay, and the fact that that number is positive. Okay, so already x is alone and we're done. There's nothing more you need to do to get x by itself. And so again, you have the option to put it as an inequality and or a interval. All right, here, how do we get the bars alone? Well, we'll find that out, but first let's go ahead and do our inequality. I'll do this one in blue. Okay. So where's the absolute value less than, exactly less than 0? Okay, so at these areas right here, and we may have to do a little bit of adjusting of this to see it. Okay, we can see that there's definitely places where it is exactly less than 0. Okay, so we can see that at 0 and at negative 2, you get where it is equal to 0. However, you're not allowed to have both sides be equal because this is not or equal. So we're going to have to think about how that's different. So what we notice is that is that there's actually two places. Either where x is less than -2, or where x is greater than 0. And see how I use the word or? That's indicating that we're going to need an or inequality, and that our or inequality should conclude with x is either less than -2 or x is greater than 0. Let's go ahead and get the bars alone and see if that happens. So I begin by subtracting 3 on both sides. So I get the absolute value of x plus 1 times -3 is less than -3. I'm now going to divide both sides by -3. Because I divide by a negative, the inequality changes directions. I bet you might have been wondering, how is it going to be an or when the inequality, that is, faces the number? Okay, so that goes to show you that you cannot make any conclusions about the solution type until the bars are alone. Some individuals may have said no solutions at the previous step because they saw less than a negative number. But again, that just gets into the idea that you cannot make a conclusion about your solution setup until the bars are alone. Now, if you consult the front of 4 and 9, what you're going to notice is that this indicates an or inequality. Okay, so how do you split this up when it's an or inequality? So either you do x plus 1 is greater than 1. See how this stays exactly the same. Or x plus 1 is less than -1. So one of them, the inequality stays the same except the bars are removed, and the other one, the inequality sign flips directions, and you have the opposite of the number on the other side. And that has to do with just the nature of absolute value. The fact that negative x plus 1 has the same absolute value as straight up x plus 1. And now I get x alone, just like it was any inequality. So I'll subtract 1. I get x is greater than 0. I subtract 1. I get x is less than -2. And then what I do is I put an or in the middle to indicate it's an or inequality. And the way you can write this is this. Now you should write right to left, or that is left to right. So I'm going to go negative infinity to -2. That's x is less than 2. Union 0 to infinity. That's how you could write it if you wanted to write it, or if you were instructed to write it as an or inequality in an interval notation setup. Okay, third example, I did want to show you one that actually does involve 0, so I think it is important to think about how does 0 work its way in, what would that look like? So I'm going to do this. So when is it greater than or equal to 0? So interestingly, this is we ask ourselves, when is this absolute value graph more than or equal to 0? And that's actually everywhere, right? When we're at, it appears, when we're at +3, this is really interesting. When we're at +3, it's actually like everywhere. But also, I think that we do need to make one adjustment to this graph, because I think this is actually the graph of negative. Based on what I'm seeing, this is actually x minus 3. So make sure you make that adjustment. X plus 3 would be on the other side, but it's not going to really have any noticeable impact in terms of the actual solution outcome. So when it's equal to 3, we've got both sides being equal to 0. But when x is more than 3 or less than 3, you're still going to have a value that's more than 0. So here we're actually going to expect all real numbers to be the solution. And we're going to work on how we know that's true. So here what I'm going to do is I'm going to multiply on both sides 2/3. 2/3 and 3/2 are going to cancel. Please, again, make sure you fix that x plus 3 is to an x minus 3. But 0 times 2/3 is still 0. There's no real impact there. And so this again would be an or inequality. Okay, you can see there's in a sense. So you could either get, see how I do this split up, you could either get that x minus 3 is greater than or equal to 0, or that x minus 3 is less than or equal to, but what's -0? it's still 0. So either you get x is greater than or equal to 3 when you add 3, or x is less than or equal to negative 3. But all numbers, that's true. You choose a number, it's either going to be greater than 3, less than 3, or equal to 3. So this is essentially equivalent to all real numbers. Now, if I had said it is only greater than 0, if I had left out that or equal to, then what it would actually be is every number but 3. And maybe in class, as like a warm-up, we'll take a little look at an example of how that works using a graph and using an equation. That would be a cool one. All right, lastly, we have this one here, and I'm just going to get creative and colorful, and I'm going to just change how this is marked up. So here we have this function, and we want to know when it is greater than 0, and you can actually see that there's actually no x's where that works, right? There are absolutely no values of x in which that is true, right? It's always going to be less than 0. So we're going to actually expect, in this particular instance, we're going to expect there to be no solutions. So let's go ahead and see what that looks like. So first we're going to get the bars alone. We're going to add 1. So 2/3 times x plus 1 is greater than 1. We multiply both sides by negative 3/2 to clear that out. Okay, biggest thing you have to remember to do, and again, this is going to be the place I think where we most get mixed up. You have to remember to flip the direction of the inequality. Why? Think about what difference that's going to make. If you don't flip the inequality, you're going to have more than a negative, and so you should conclude all real numbers is your solution. But actually, this is the exact opposite. Instead of everything being a solution, because we're less than a negative, actually nothing is a solution. So you're actually on the complete opposite end of the idea just by having the flipping not occur. Okay, so please make sure you understood what I did there. Rewind, pause, do whatever you need to do. And then in a moment, we're going to move on to connecting this to the graphs. All right, so connecting it to the graphs, I just want to recap. Remember, this turned into be an and inequality. This turned out to be an or inequality. This turned out to be all real numbers. This turned out to be no solution. So this and inequality, we ended up with being from -3 to 3, including the endpoints. So we put our dots on the end, and we shade in between. You're only shading what is true. So you're shading in between. Okay, -3 to 3. The other one is x is, and let's make note, greater than 0 or less than -2. So open dot on the 0, open dot on the -2, or opposite. These should be going away from each other. And hopefully this kind of starting to come back to you from when we talked about or inequalities. All right, all real numbers, you're going to shade everything. And again, don't forget with or and stuff like this, if it goes beyond the number line, you do have to put arrows on the end. So you can see I'm shading this whole number line, arrows on both ends. That's understood to be all real numbers, okay? It's not infinite solutions because there's always infinite solutions as long as there's at least something. And the last one, no solutions, we literally, you're going to love this, we literally leave it blank because not a single number will ever work here. Okay, so just a little recap of what an and looks like, an or looks like, an infinite solution, or all real numbers I should say, and no solution. Okay, so please make sure at this point you've completed up to this on the back of 4.9. Then we're going to take a quick second and we're going to actually do some ones for you to try. All right, so this is like a we do, but I'm actually going to kind of make this more of like a you do. So thinking about what we've done so far, what I'd like you to do for both of these, I'd like you to pause the video. I'd like you to follow the steps to solve the inequality. Solve that inequality fully out. Graph out the solutions on the number lines given. And then when you're ready, unpause, and you can see if we both got the same thing. All right, let's go ahead and break this one down. So here we can see the bars are alone, nothing to the left, nothing to the right. So I'm going to ask myself, what kind of solution should I have? So based on what we know on the front, and again, we're really rocking a lot of open notes this year, so we know that we can have that accessible and inequality. Okay, so it's going to be between two numbers. And if you think about it, what numbers have an absolute value that's either less than or equal to 18? That would be all the numbers between negative 18 and positive 18. So negative 18, negative 17, negative 16, all the way up to positive 16, positive 17, positive 18. Stop. Okay? So what we know is that we're going to go from negative 18, 6n, because when I think all the numbers from negative 18 to 18, that like verbally is an and inequality. Now I'm going to divide all three sides by 6. 6, 6, 6. Negative 18 divided by 6 is 3. 6n divided by 6 is n. Positive 18 divided by 6 is positive 3. And I'm done. Now I'm going to graph it with a closed dot on the negative 3, a closed dot on the positive 3, and I'm going to shade in between negative 3 and positive 3. Okay, there we go. We have this one done. Okay, on the right, again, similarly, I do have the bars alone. I'm in bars alona. So I'm going to ask myself, what numbers have an absolute value of less than or equal to 8? And the answer is all the numbers that are less than or equal to 8 and more than or equal to negative 8. From negative 8, that is, to 8. Right? If I go negative 9, that absolute value is equal to 9. That's more than 8. That's not a solution. If I go 10, positive 10, that's not a solution because that absolute value is 10. That's also more than negative 8. We want less than or equal to negative 8. Okay, so here's our p plus 4. How do we get p by itself? We subtract 4. Again, you remember to subtract 4 from all three parts. And also remember what dictates what you're adding or subtracting. You always look to where the letter is. A lot of people add 8 on all three sides because they're trying to like get rid of this 8 on the left. That's not going to help you with p. Or getting that is whatever letter it is alone, look to where the letter is. So negative 8 minus 4, that's negative 12. And then 8 minus 4, that is 4. And just as a quick check, negative 8 plus 4, if I plug in, that is negative 12 plus 4, if I plug in my smaller number, negative 12 plus 4, that's equal to negative 8. That's the lowest you can go and have an absolute value that is less than or equal to 8 because it's equal to 8. And I'm plugging in 4, gives me 4 plus 4 or 8, and that's the highest I can go while maintaining that absolute value. So I'm going to again put my closed dot, and again close because it's or equal to. And I'm going to put my closed dot on the positive 4. Again, because the or equal to, it's a closed, and it's an and, so I'm going to shade what is in between. All right, folks, so if needed, please feel free to go back, rewind, recap anything needed, and then we'll go on by talking about where we're going to go from here today. All right, folks, so what you need to do going forward from here is you need to work on this sheet. According to the famous TV critic, Boob Tube, why is television called a communications medium? So you're going to complete the absolute value equations and inequalities. You must show all work for full credit, okay? And if no work, I will associate with no credit. So you must have work and you must include work, no exceptions. So complete the equations and inequalities, and then what you're going to do is you're going to notice the two letters next to the answer, fill them in above the where the problem number is. So for example, when you solve problem 1, put the two letters that are next to the answer above where you see the number 1. Okay? You're going to do that until you fill out the riddle. Again, you must show work for credit. If I don't see work with the solutions, you are not going to receive credit. I'm going to give you a 0. You can use the back of this sheet to do your work. You can use another piece of paper, but you must show work. Be prepared for us to recap next time I see you. We'll continue to work through this and really develop our skills. Thanks so much, folks. Keep up the positive attitude, and remember that you can do it. Thanks so much. I'll see you next time. Have a wonderful day, and don't forget to love math.